Sorry, my last video cut me off. So if you take the limit of the f of x graph as we're approaching -3, that looks like it's going to hit at 3. The g of x graph as we approach -3 looks like 4. And subtracting, you get -1. Okay, so remember that when we have powers, what we're going to do is we're going to take the limit of just the function, and then we're going to raise the entire answer to the second power, or the outside power, whatever that may be. So f of x graph is the one on the left. What are we approaching when we're approaching 2? Notice there's no plus or minus, so it just means from both directions. When you come from the left side, you approach -1. But when you come from the right side, you approach 1. Since these points do not match up, the limit does not exist. Okay? In order to take a limit from both directions, they have to meet at the same point in order to have a limit. So this is one that we get D and E. And I can't square it because what's D and E squared? Nothing, it's just D and E. Okay. E, we've got a constant and we have a quotient. So I'm going to split it up. I'm going to put -6 on the outside. The limit as x approaches -3 of f of x, and then divide by the limit as x approaches -3 for f of x is on the bottom. Shoot, g of x goes up here. Okay, so let's start with the top. G of x is the right graph, and we're approaching -3, which looks like it's approaching 4 from both directions. So that would be -6 times 4 in your numerator. For f of x, also approaching -3, appears to be 3. And we'll simplify. It's -24 divided by 3, which is -8. Okay, so last one here, we've got a product. And again, you're just going to use those properties to break it up and say that I'm going to find the limit for f of x and multiply by the limit for g of x. All right, to my graphs. So as x approaches 3, so here's 3. As I approach 3 from the left and the right, I'm hitting a y value of 3. And then for g of x, 3 would be down here. From the left and the right are both approaching -2. And so your answer looks like it's going to be -6. Okay, so we're going to get into more like theories and rules and things like that. So here's another theorem to help you solve limits without graphs. And this is called the substitution theorem. So it says if you have a function that is either a polynomial, which example A is a polynomial, or a rational function. A rational function is something that's like a function divided by another function, like example B. See, it's like a fraction. C would also be considered a rational function because it's got a radical over top. Then it says that the limit of the function as you're approaching some value is equal to f of c. F of c just means that that would be like the y value at that certain point. So what this will allow you to do is take a shortcut. And it says that if you've got a polynomial or if you've got a rational function, essentially you can just take whatever value the limit is asking you to approach and you can substitute it in for x in the equation, and that will give you your limit. Okay? Basically, the theory behind this is that polynomial functions are continuous, which means they don't have any holes in them or any breaks in them. So the limit, you've got a smooth curve, so the limit's going to just be whatever point is on that curve. Okay, so if I go back and look at the graphs we were dealing with, you're not going to have any of this weird stuff going on. Okay, no holes in the graph, no jumps, things like that. And then rational functions are also continuous. except sometimes they're not continuous when the denominator equals 0, right? We've learned that since the beginning of the year. That's why there's this little extra note. It says, provided that the value of the denominator does not equal 0. So if you're in a situation where you're plugging a number in and it makes the denominator 0, this substitution theorem is invalid. And I have a trick for how to deal with it, but that's coming next. So let's just practice substitution theorem. So what you're going to do is you're going to say, how do I find this limit without graphing? Is it a polynomial? Yes. So then I can just take the -1 and plug it in for x and solve. Okay, again, that's because the limit is equal to the y value on the curve because the curve is a smooth curve. There's no holes in the graph or anything. So we're going to do the math. -1 to the third is -1. This would be -1 squared is +1 times 2 would be 2. Plus 5 plus 4, 9, 10, 11, 10. Is anybody getting 10 for that? Yeah, 10 looks like it's the right answer. So this limit would be equal to 10. Okay. B, is it a rational function? Yes, because it's got a function divided by another function. So you can do your substitution method. Just do a quick check and make sure that the number you're plugging in does not give you a 0 in the denominator, which it doesn't because 3 plus 3 would be 6. So we're going to do substitution, which gives me 3 squared minus 6 times 3 plus 5 over 3 plus 3. And do the math, that would be 9 minus 18 plus 5 over 6. 9 minus 18 is -9 plus 5 is what? -4. And that reduces to -2/3. So your limit is equal to -2/3. Okay. And then C, same thing. So we're going to plug in. All right, let's see. 2 to the third is 8 times 3 would be 24 minus 4 plus 5. 24 minus 4 is 20. So what is that? 25, which is 5. Okay, substitution theorem. Nice and simple. All right, so here is your like exceptions to the rule. So substitution theorem doesn't always work because sometimes what happens is when you plug in that number to do substitution theorem, you end up getting a 0 in the denominator. And then you're like, well, now what? So what you would do is if you are trying to plug and chug and you get a 0 in the denominator, stop and do this cancellation technique. So the cancellation technique is basically you doing algebra to simplify the rational expression before you plug anything in. So right now I can tell if I plugged in 2, I would get a 0 in the denominator. So I have to stop and say, what can I do algebraically to make this simpler? And so what I know that I can do is I can factor. The top will factor to x plus 3 and x minus 2. The bottom will factor to x minus 2 times x plus 2, right? And so it's called the cancellation technique because you should be able to cancel something and will leave you with something that's smaller, simpler, whatever you want to call it, than the original problem. So what I have now is I have a simplified version of the original equation. And now I'm going to try plugging in the number 2 to find the limit again. So now I'm going to essentially try the substitution method again. So I would have 2 be plugging in 2 for x. And now I'm able to get an answer that does not have a 0 in the denominator. Okay, so let's try a few more. B, again, I'm going to check and see if I can get an answer without doing the cancellation. So I'm going to go to the denominator because that's where our restrictions lie, and I'm going to plug in 3. So 3 squared would be 9, plus 6 is 15, minus 15. So we do get 0 again, right? So we need to do our cancellation, which means you're going to try to factor, and hopefully something will cancel. So on the top, looks like I'm going to need x minus 8 and x minus 3 to factor that. And then the bottom would be x plus 5 and x minus 3. And I am able to cancel x minus 3 with x minus 3. So let's see what we've got left. All right, so here's our simplified equation, and we can do our plug and chug. And it looks like it's going to work because we're not getting a 0 in the denominator again. So I am going to get negative 5 on top and 8 on the bottom, and that is my limit. Okay, so negative 5/8. Okay, on C, same situation, you just got a radical that you're dealing with. You are still gonna be able to hopefully factor and cancel. I am gonna do the factoring step because I know that when I plug 4 in, I do get a 0 in the denominator. So let's see what we can do. I'll leave the radical there for now. And then that's gonna give me, let's see, x minus 4, x plus 8. That's how you would factor that. And then the x minus 4s on the top and the bottom cancel. And then you remember your rule with radicals. You're allowed to take the radical and move it to the outside, which means you can do the limit of everything on the inside of your function first, and then just square root the answer when you're done. So that means I'm going to plug 4 in, which would give me 12. And my answer would need square rooted, and so that means square root of 12 is my solution, but that will break down into 2 radical 3, so that would be a better answer. Okay. Example D is more of the same, except this one is here primarily to make sure you remember different methods for factoring. Like the numerator is factorable, but it's a GCF, so you can take an x out of each term. The bottom is a difference of squares, so that would be x minus 3, x plus 3. And then cancel, cancel. So you've got the limit as x approaches 3 of x over x plus 3. And now you can do your plug and chug, which gives you 3 over 6. So 1/2 would be your limit.